For the first problem on constant velocity, which was the Swiper Sweeper video, to find the displacement of the rider after one revolution is easy to explain. Displacement is the change in position. Since the rider is going in a circle, there's displacement after one complete revolution is 0, since they end up where they started. Next, we had to estimate the distance traveled by the riders after one complete revolution. To estimate this, we had to try to figure out the size of the circle that the car was traveling on. After doing that, we came to the conclusion that the track was around 40 feet. In order to answer the next question, we had to convert 40 feet into meters. To do this, we times 0.304 meters by 40 feet. This gave us 12.16 meters. Now we needed to find the average speed of the rider after one revolution. For us to figure this out, you divide the distance over the time it took for the rider to complete one revolution. Even though the mechanism that moves all the cars moves at a constant speed, the cars get whipped around the end so quickly because it is curving, so it whips for the car to get to the other side. Pepsi Climb video, we analyzed the motion of the roller coaster going up the hill. We figured out the roller coaster was traveling at a constant speed. We were able to conclude this because when we graphed the points, the graph was a straight line going from left to right. Because it was traveling at a constant speed, we had to find the velocity. To find the velocity, divide displacement over time. After dividing the two, we found out the velocity was negative 2.101 meters per second.
For the acceleration of the Fairly Odd Drop video, we had to find the car's acceleration. Because acceleration is distance over time, first we had to take Vf minus Vi divided by the time, which is also the velocity. To do this, we imported the video into Video Physics and took the motion map data. Before we moved it into graphical, we had to set the scale of the car and the distance, which was about 4 feet. Then, because we needed it to be in meters, we had to multiply by 0.34. After this, we could import the video into graphical. In graphical, we used the data file and turned on statistics, and then it showed us that we had an acceleration of 0.8684. This is how we found the acceleration for the Fairly Odd Drop video. For the acceleration of the Fairly Odd Drop video, we had to find the car's acceleration. Because acceleration is distance over time, first we had to take Vf minus Vi divided by the time, which is also the velocity. To do this, we imported the video into Video Physics and took the motion map data. Before we moved it into graphical, we had to set the scale of the car and the distance, which was about 4 feet. Then, because we needed it to be in meters, we had to multiply by 0.34. After this, we could import the video into graphical. In graphical, we used the data file and turned on statistics, and then it showed us that we had an acceleration of 0.8684. This is how we found the acceleration for the Fairly Odd Drop video. One of my little brother's favorite rides at Mall of America is the Pepsi ride. I think this is because of how calm and how not lurchy the braking at the end of the ride is. If you couldn't tell, that was definitely sarcasm. You get a headache almost every time from knocking your head around at the very end. It is the least smooth ride in the park, according to my family. For our first problem that we did was focused on acceleration, and we did it on the Pepsi braking video. For this, we used the video from Mr. Myers and had to track the deceleration of the last car on the roller coaster. First, we tried to track it using the front car, but when the ride finished, you couldn't tell that the car had even slowed down. This is because the centripetal force of the different loops and spins along the roller coaster will impact the timing and the speed of the first and last car at different rates. As the car nears the end of the track, there are multiple sets of mini brakes. There is also a mini incline of the hill, which is used to stop the ride from going through the end and smashing into the next car. For this section, we looked at the back car was more beneficial, so then we could clearly distinct the time and the Vf minus Vi, which was about 35 seconds. This resulted in a slope of negative 1.76. To get the acceleration from the slope, we had to use the F equals ma formula. This worked, and we found that we had a slope of negative 0.56, just over 1/2. It was negative because the ride was braking, so the slope would be a deceleration. And from this, you can see the deceleration of this ride. For the free fall of acceleration, we chose to do number 10, which was the Fairly Odd Curve video. We had to describe the sources and keep the ride on track. which were the forces. After looking at the ride and the video, we concluded that it was gravity, normal, and friction forces. Gravity is used to keep the car on the track so it doesn't fly off, resulting in everyone dead. Normal force is a force against gravity, and the friction force is a force that keeps the riders and the cars on the track, propelling it forward or lurching it to go backwards or even helping it brake. With this also comes a little bit of applied force. Because of the path, there is a chain and a course running all the way through. Helping with this, there is inertia that is applied all the way through the ride, but especially at the very end and through the loop-de-loops.
Forces, we took a screenshot of the Avatar Airbender at its highest point. Then we made a force diagram and labeled it with all the forces acting on the skateboard car. Here's what we figured out. The only forces present are of course, gravity, since the skateboard car isn't floating up into the sky. There's also normal, which keeps it attached to the track that is attached to the ground that is attached to the earth. For the energy, we took 4 screenshots from the SpongeBob Drop Loop video to show the car at different positions. We took the 4 screenshots and placed them into Notability and drew energy charts for each of the positions. Here's what we found.
That video was a girl holding onto a rope swing. This had to do with tension force. She let go too early, which meant the tension flipped. The lady fell on her head, and in our actual conclusion, this project was fun and we learned a lot.